So I'm going to talk about a way of implementing cooperative threads for Edsim51. And here's an outline for this. So first, let's just do a quick review. Okay. So subroutines versus functions versus threads. So you remember subroutines, right? We did that. We wrote the code in assembly. So the word subroutine actually is an assembly language concept. And what it does is, instead of having a copy of the code, you do a call. In 8051 case, there's L call or A call. It just depends on how many bytes that instruction, how far away it is. So one version limits you to the first 4K, the other version could be anywhere in the 64K space. Why? Because they want to be able to really pack the code very tightly. Okay. So subroutine is really, you might call assembly language or machine language level concept. It's supported directly by the machine instruction in the form of call and return. And it's the hardware is supported because when you do the instruction, it has the side effect of pushing the return address on the stack. And when you do the return, it pops the return address off the stack back into the program counter, right? So you all remember that. So that means there has to be a stack, and the hardware does make use of it. Okay. So you don't say push or pop in the case of call and return. It just does it as part of its semantic. Right? And now a subroutine is much simpler than a function call. Why? Because a subroutine just jumps there and then runs something and then comes back. What if you want to pass parameters? Well, you have to then make some agreement. Remember, we did pass our parameter in the accumulator, right? In the display, you put the digit you want to display in the accumulator before you make the subroutine call. And then the other side assumes, anybody who wants to call me puts the argument in the accumulator. And that's an agreement between the caller and callee. Okay? And then upon return, if you want to return any value, well, you could use the accumulator, you could use a register, whatever. As long as both sides agree, then you're okay, right? Now, but then that is something assembly language doesn't tell you very much. It's knowledge that the programmer has and has to kind of follow, right? It's a rule in there. Assembly doesn't tell you anything like that. So that's why in a slightly higher level language like C, they make this explicit, right? So as you know, when you define a function in C, you define it in maybe like the .h file. You have the type signature, right? It says what the return type is, the name of the function, and the types of each argument, right? And so that itself is spelling out the agreement between the caller and callee, right? And if the caller doesn't pass the arguments as required by the callee, then the compiler gives you an error. It says, no, it expects this argument or that. Or maybe it knows how to convert between the floating point and integer, then the compiler just handles it, right? Anyway, so you can think of a function as this kind of higher level wrapper around subroutine calls. Underneath it, yes, it is a subroutine call, but it just adds nice features to prevent little mistakes, like not knowing the agreement between caller and callee, not knowing the type. Right? So, and moreover, the function concept, which is defined by the C language, also supports right, not just passing parameters, but return values, but also these auto local variables, right? So that means it builds a stack frame and then allocates space for the local variables during its execution. Upon return, tears down the stack frame, and then those go away. Now, when you write code in assembly, from time to time you have to make use of these registers, right? Could be R0, R1, R2 through R7, sometimes accumulator, sometimes the B register. Well, if you read the 8051 instruction set manual, you know, like A and B are sometimes used together when you do a multiply and other things, right? And also, like certain registers R0 and R1 can be used as pointers to your data. So if you want to do a pointer to data and then walk an array, copy from one array to another, just for I, right? So then you have to use R0 and R1. So, but different root of code needs to make use of these registers. So what happens? So if you remember from our very early assembly language program, we were using accumulator as the loop I variable, as well as for passing parameter and handling return value. Now, upon a call, what I did was a push, if you remember. Why? Because the callee, that is the function I'm calling, is going to trash certain registers, right? It's going to just assume it can use these registers. But what if those are registers I still want to use? Then somebody has to save them, right? So in that case, as the caller, I say, okay, I know which registers I want preserved, so I don't trust the callee. So I'm just going to push things on my stack and then call the callee. The callee can do whatever it wants, and when it returns, nothing matters anyway. But when I want to recover those variables, then I pop them off the stack. Okay, so that's an example of saving registers. And I don't mean just the R0 to R7, but also accumulator, B register, maybe data pointer as well. And so in that case, as the caller, I save what I want. And then callee can use whatever they want. But then the thing though is that what if the callee doesn't really use the register I saved? That means I kind of did extra work unnecessarily, right? So like if I want to use, if I save my accumulator, but the callee never uses the accumulator, it's kind of, I did extra work unnecessarily, right? But the other way around is, okay, I'm going to trust the callee. So I don't save anything, the callee. If they want to use a register, they better save it. Right? Then the callee can push a bunch of registers, and then before using, and then upon return, it restores those, and then return back to me. But then that has an opposite problem. What if I wasn't using those registers anyway? So they were saving for no reason, right? So that's always an issue that will come back. But we'll discuss this some more. Anyway, so that's what a function does. So the compiler actually defines the conventions for passing parameters, passing return values back, constructing the stack frame for auto-local variables, and also for saving and restoring registers. Okay, that's what a compiler does to a function. And that's why in earlier days, when people who were used to programming assembly, they look at a language like C and say, oh, no, what do you mean? You're doing this much work? I was just doing, I know my convention. I'm just passing everything in register, and I know what gets used, what's not. I don't have to do this extra push and pop. Yes, that's true. And you can craft things to run very fast in assembly. But then you pay a price to it because your code is very difficult to maintain that way. You have to know all these implicit rules. That's why, yes, in a language like C, yes, you do that little bit of extra work, but then your code is much more maintainable, okay? Because compiler handles a lot of these lower level bookkeeping things. Now, threads, on the other hand, is something that requires runtime support. So you can think of the functions in C as a compile time abstraction. That has a little bit of runtime overhead. Thread, on the other hand, is a runtime abstraction in the sense that it is an artificial concept or software concept, even though it still makes use of some of the features you see, including subroutines, including functions. Why? Because by default, if you just run the hardware, it's just assuming the program counter and a stack, right? It's just assuming a single threaded. But we if we run threads, then that means you're using software concepts to implement multiple threads of execution. And so that means you are dividing up the space into these what's called execution contexts. Each one has its own copy of the stack space, its own set of register values, its own program counter value. Right? And so this allows multiple threads to run concurrently but share these resources. Okay, so just a quick review again, subroutine call. On 8051, you have lcall, which is a native instruction. There's another one called acall, which is absolute call, and it saves you 1 byte. So 1 byte, what's the big deal? Well, on a little machine, it's a big deal. But acall just limits the range you can do, and lcall is more general. So anyway, so you do an lcall, and remember what we were doing is our own convention. We wanted to pass parameters in accumulator. That's not necessarily how a compiler would do it, but if we write it in assembly, we do whatever we want, right? So it does an lcall to display. At this time, it doesn't just go there. It pushes the return address on the stack as part of the lcall, okay? And what return address does it push? Does it push the return address of lcall itself? No, it's the instruction after lcall, because that's where it returns to, right? Otherwise, it keeps returning to lcall and you never finish. It just keeps, right? So it pushes the instruction address after this lcall, right? So that would be the address for ljump. So it jumps to display with the return address on the stack. There's the move, right? That dptr, and then that's the lookup table. And then once it looks up, then there's a move to P1. That's how we did the LED, right? Then there's a return to main, right? Return basically does PC gets pop, right? Pop from the hardware stack. And this stack is maintained by the processor. Okay, so there is a stack pointer called SP, and then that's how it allows the call to happen and return, right? So now PC itself is not a special function register, so you're not supposed to say move PCs, comma, something. Well, you do that by doing a jump, right? Or a call. Lcall has a side effect. Now, and also return is one that modifies PC, but otherwise you can't just do a direct move into PC. And you can't read out of it. But you can do it indirectly. Why? Because when you do a return, guess what? It puts the PC value, or at least something close enough, right, on the stack. So if you really want, you can go and read a stack to read the PC value, right? By that time, it already jumped elsewhere, but at least you get a snapshot. Or you can say, I want to return or jump to this location. Well, if you do lcall or jump, these are hardwired in the instruction, so you can't make a variable. So jump to this variable location. But what can you do? Well, if you want to do jump to a variable location, easy. All you do is push that address on the stack and do a return. Get it? So that way, it couldn't tell that it was pushed by a call instruction or by your own push. Okay, so that's a trick. So, and that's the same trick used by the threads package. When you want to switch threads, how do you know how to restore, right? So when you first set it up, it could be a different thread. So you can't rely on the hardwired address, or you can't call, but instead you have to do a return with the address you want. So that's a lot like jumping to a variable location, right? The trick is you push the location you want to jump to and do a return instruction, even though there wasn't necessarily a call to match it. That's okay, as long as the stack looks like the return address, it'll be happy to return to it, okay? And then pops it off, then everything is acting normally. So that's a trick you gotta keep in mind. So anyway, so lcall, ljump, return, RETI. RETI, as you remember, return from an interrupt service routine, right? but you really don't get to do a move, but you don't need to. So subroutine calls, ISA supported, so L call, A call instructions basically do a push of the PC for next instruction, then do a jump. Return is to pop return address from PC and then into PC from the stack, right? And parameter passing, well, that's something an instruction set architecture doesn't necessarily have any support for. Some RISC architectures, what they do is they say, well, there are certain registers, like A0, A1, A2, you just have to use them for passing parameters. Okay, fine. 8051 doesn't really dictate anything. Whoever is calling, the caller, callee just have to agree. If you want to pass in parameter in A, then the other guy takes it from A. Return from in A, takes it from A. Okay, just an agreement, right? Nobody says anything. You could use registers, R0, R7, right? Or you could do DPL, DPH, do stack, whatever. It doesn't, I mean, it's just an agreement. It's a protocol between caller and callee. Now, what about stack pointer? We've been talking about stack pointer for some time. Just where is it and how does it work? So stack pointer is a special function register, right? And all special function registers have address between 80 hex and FF hex. Now this one is at 81 hex, but you don't have to know that. And so when you power it on, what does a stack pointer pointing at? Well, it's pointing at address 7 hex. Like what? 7? And that's kind of a strange number. Why would you want to point at 7? Well, 8051 hardware stack is kind of funny in that, as you have seen from textbook elsewhere, stack pointers usually go from high address and then grow towards the low address. Every time you push, it actually decrements and then pushes on the stack towards, right? And then when you want to pop, it goes toward the higher address. And the reason they did that was because they want one region for your dynamic memory allocation, namely heap, and they don't want stack and heap to collide. That's why they move it as far as possible out of the way. Hopefully the two never collide, right? But not on 8051. They assume, well, you don't do that much dynamic memory allocation. You know what you're doing, and memory is tiny anyway. So it's okay. We just grow from lower memory up. So it's kind of opposite from, Intel does a bunch of things opposite from everybody else, like little endian bit order, or byte order. So most everybody do big endian byte order. Intel does little endian. Anyway. So now the stack pointer is pointing at the top of the stack, but what it does is what's called, when you do push, it does the pre-increment push. And then when it does the pop, it's the post-decrement pop. What does that mean? So in C, you know there's a plus plus operator, right? You can do the plus plus in front of a variable or behind a variable. What's the difference? So pre-increment means you increment that variable first before you access this value. Same thing with the pointer. So stack is at 7. So if it's pre-increment, what does that mean? 7 is currently empty, or stack is empty because stack starts at 8. And if you want to push, then you pre-increments stack pointer. Now it's 8. And then 8 is now the location where you write the value, right? So it's pre-increment, post-decrement. So the first value you push goes into location 8. And then next value, location 9, next value 10, 11, and so forth. And when you pop, you take what the stack pointer is pointing at, take it out, and then decrement. So that's post-decrement, okay? So keep that in mind. And so that's why it's at 7. Why is 7? Because registers 0 through register 7, R0 through R7, occupy location 0 through 7. And if it's empty, then it points at 7 because anytime you do a push, it pre-increments, so it moves to location 8. So it's not going to overwrite register R7, assuming it doesn't use any register window, okay? Now, so that's the stack. And the stack, as a special function register, means you could actually change it. You can do SP, gets some other address. Wow, isn't that kind of dangerous? Yes, it is. So you got to know what you're doing. But then that's how we can do stack switching between threads. We don't necessarily use the concept of heap, but yeah, if you don't follow the memory allocation, certainly anything bad could happen. You could keep popping stack with underflow, and then of course it gets into the globals. Heap is really for dynamic memory allocation, but globals. Right? So yeah, certainly, if you're not careful, stack can certainly overflow or underflow. So you got to be very careful. Now, so this SP location can be saved and modified just like any other register, right? So that's easy, but you have to know what you're doing. Now, what about the address, right? So when you do like a call, right, it pushes return address. Now, in what order does it push? It's 2 bytes, right? Because it's code address. Code space is 64K, so it's 2 bytes. So remember, Intel is a little byte endian, a little endian architecture, byte order, right? So that means it pushes the lower order address first, then higher order address. That's the memory layout. So on the stack, right now it's at 7. So if I do a call to main, and main has 2 byte address, then address 8 and 9 will be together the return address from where I call main, right? But address is 2 bytes. There's lower order byte, higher order byte, right? Lower order byte would be the lowest significant one, so 0 through whichever, and higher order byte. So it pushes the lower order byte first, followed by the higher order byte, because that's the little endian byte order, okay? So we'll come back to this a few times. Okay, so now function call. If you do SDCC and generate code, this is what it might look like, okay? So when you do move, main like this, and char I, where is char I allocated? Well, in this case, it's register allocation. So R7 gets 0, right? That's where I gets 0, I less than 10. So R7 gets 0, and then there is that label again. Move DPL, comma R7. So DPL gets R7. Why would you do that? Well, if you remember, SDCC actually passes its parameters in DPL, DPH, and then a few others. But for now, we'll just do this. So DPL, if it fits, and if it doesn't fit, DPL, then DPH. Right? So R7 is our local variable I. And it gets passed in DPL, and then does the call to display LED, right? And then, before the call, it does the push of AR7. Remember what AR7 is? That's the absolute address of register 7. Why? Because there's restrictions on the push and pop instructions. You can't do a push register or pop register. You have to push the direct address of the register. So assuming you're not using any register window, then R7 has the address AR7. That's the symbolic name for address 7, right? And you can take a look at the assembly, or actually machine code if you really want to. There's the L call, right? So that means it's saving its local variables before the call. And then after the call returns, comes back here, pops it, restores the I. Okay, that's what a function call has to do. And then what does it do after it returns? So it continues here, inc R7. That looks kind of familiar, doesn't it? So that's the plus plus. Okay, so C language gets the plus plus idea from the inc instruction. Well, not necessarily 8051 from the PDP-11, but yeah, PDP-11 has inc. In fact, most CISC architectures in those days love to have an inc. Why? It's used so much. It's worth having an instruction to save a few bytes, and it makes it more fun to write assembly. So anyway, so it does a clear of C and move R7 into A, and then X OR with this, and then let's do a sub of hex 8A. So it's like, wow, doing all that. Well, it's really just testing if I is less than 10. Okay, so, but you can write it in different ways. The compiler just has clever ways to do this. And JC, the jump is carry, right? So then it goes back to the loop, right? And then otherwise return from main. Okay, so and then display LED, what does it do? It does the L call to LD7 segment, and well, it does a little optimization because incoming parameters in DPL, and then when you do it, then you have to make a function call, right? And that's already in DPL, so there's no need to do a DPL copy to DPL itself. So it calls the LED7 segment, and the LED7 segment does that lookup, right? So that's a lookup. Put DPL into A, and then there's a DPTR plus, right? And then the return value is passed in DPL. Unlike what we did the A because we could save a few instructions. Compiler isn't that smart, but not bad. Okay, so return value also goes in DPL. Returns back to display LED. DPL already has the return value, so you move that into P1, and that displays that LED 7 segment LED, and then does a return. Okay, so you should be able to understand every single instruction here. This is a relatively simple program. Okay, I mean, other than this one, yeah, you can take some time to figure out, but that's not the main point. The control transfer is the main point, and also passing parameters and everything. Returns to the caller. Now, function calls. So compiler does these things. Basically, define the convention for passing parameters, convention for return value. So it's a wrapper around lcall return. That is still there. You can still clearly see those concepts as part of the control transfer. It does define convention for saving, restoring registers, passing parameters, allocating, deallocating local, auto-local variables, right? And in SDCC, it uses DPL, DPH for passing parameters and return. And it's, why you just gotta read their rationale, but I think it's not bad. It's practical. Other compilers can use different conventions. So I've seen other compilers like Kyle and what is it? So there are a few compilers. They do different things, but some smarter than others. Okay, so here's just more explanation in case you miss, right? So I get 0, that's the R7 gets 0, and then label parameter is passed in DPL, push, call, pop, right? Restoring that I. Ink is R7, clear, and that's really the I is less than 10 test. Okay. And then in the return value, right? So the DPL is both the parameter register and the return value register, right? So that way it actually saves a lot of copying, and the return value is used directly for writing into P1, right? And then this one, we've seen this before, right? DPL, that was the parameter coming in, but then we need to do a table lookup, which is A plus DPTR, right? So DPTR, and then is loaded with the base address of this lookup table. And the label just looks kind of funny in here. But then once you have it, add the offset to the base register, and then the lookup value goes into A, and then this move of A to DPL, that's to return in the register, right? And then return. Okay, so you gotta be very clear on how function calls work. Now, assuming you're all clear on how functions work, let's talk about threads. Threads basically allow you to support this kind of function abstraction or even just subroutine abstraction, but function abstraction really, because you're going to write it in C, so we have to follow the C or SDCC calling convention. So it's really to maintain multiple contexts, right? Where a context is defined by the set of register values and certain SFRs. So R0 through R7, now accumulator. Now I write as ACC as opposed to A because A is when the instruction implicitly encodes that register, but ACC is the explicit SFR name for the accumulator. B is kind of auxiliary register you use for like division or any temporary variable, that's okay too. DPTR, you know, DPL, DPH concatenated. PSW, that actually contains a number of different little bit registers, including your carry bit, including your register window selection, among others. And we'll take a look in a little bit. Stack pointer itself also part of the context. And the stack space, that basically you reserve it, and so it continues to exist. So that when you switch thread, it actually uses another stack space. And then program counter value has to be saved, right? And wherever it left off, whether you voluntarily or involuntarily, that has to be saved. And you could probably guess where you get that from, the stack, okay? And the threads do share everything else. They share the same code. They share. They have the same access to the memory, whether it's globals or a heap and everything. But they're really only supposed to touch their own stack. Okay. There's no protection, so everybody had better behave, or else bad things can happen. But that's okay. I think protection you kind of have to rely on hardware to do anyway. So the principle is the same. Even if you do it on a protected, memory protected machine, most of the code is the same. The only difference is you enable these bounds registers. That's one or two extra steps. No big deal. That's the easy part. Hard part is how do you manage the context. Right? Okay, so threads. I talked about two kinds of threads. So there's cooperative threads and preemptive threads. And book that actually doesn't talk about cooperative threads in the threads chapter, not until they start talking about scheduling. But I think that this concept is actually kind of important. A cooperative thread, I mean, you probably should know by now, is more like what Python generators do, but at a lower level, right? Remember Python generator is like a function call, except you can do a yield instead of a return. When it yields, it basically gives up control, lets somebody else run for a while, and then somebody can continue with it by calling next or by doing ascend, right? And then it picks up where it leaves off and then continues running. So that's a lot like what cooperative threads do. But Python certainly nicer syntax and everything. Now, when you do this in C, you have to build up a little bit more. You probably don't get the intermediate return values through yield, but that's okay. That we could always work on that. So cooperative threads are a little easier, but by no means easy. There's just a lot of details you have to get right. Certainly a lot easier. And there's really not race condition you have to worry about. You have to worry about race conditions when you start doing preemptive threads. Okay. So here, at least things behave in much more predictable ways. It does give you the ability to switch, but they have to do it voluntarily. So each thread has to explicitly do a yield, just like Python yield, right? Generator yield. What if they don't yield? They just keep hogging the CPU, and then the other thread just starts. Okay, so that's one downside with cooperative threads. But we'll start with cooperative. And then upgrading cooperative to preemptive. That's actually a little easier than just doing it directly. So once you have cooperative working, preemptive makes a lot more sense. And all you have to do is really tie it to the timer interrupt. But still, it's a little tricky, very intricate. So you gotta know everything is all matched up. And you have race conditions when you do preemptive type of threads, okay? But for now, let's just do cooperative. Preempt is certainly trickier, and interrupts work kind of in funny ways, but once you are comfortable with interrupts, it's really not that hard. And preemptive certainly is nice because you can forget about yielding and processor just steals control back, gives it to somebody else, run for a while, and then you get to run. So you don't have to insert these yields throughout your program, and everybody gets their share. Well, supposedly. You'll see some funny examples where it looks like, hey, everybody should run, but still you get some kind of starvation problem. So, hey, looks fair. Everybody, it's called round robin scheduling. I'm doing round robin, but how come some threads never get to run? You'll see some examples of that. So, preemptive is really tricky. Okay, so anyway, this whole chapter is just on this kind of issue. Anyway, then there's switching policy, right? So this kind of scheduling policy comes later. So in fact, next week we'll talk about scheduling. They call CPU scheduling, so presumably encompasses processes, threads, and all that, right? So scheduling is really more of a policy in the sense that you decide which one to pick to run next. That can be separated from dispatching, which is the mechanism. Dispatching is the scheduler, you tell me which one, then I'm the one actually doing it. I'm doing switching. That's the dispatcher's job. And we will do something simple to begin with, round robin. That just means everybody gets a turn. One one thread, then when they yield to the next one, and then you go in a circle, right? And that's easy to do, but that's not necessarily the best one, as you'll see in the next chapter and so forth. Now, so we'll come back to our producer and consumer example. You better try this in many different ways I have given you. By now, you should be very comfortable with how this works, can explain both the preemptive and cooperative version. And so I'm cooperative in the sense of Python, preemptive Python, or when you do share memory, or even like a message passing, right? So you know all these options. For now, when you're doing threads, we're just going to assume share memory because that's the efficient way. You just deposit into the memory and then figure out the other guy will come and pick it up some other time. No need for a separate call or copying or whatever, right? So now if you do producer consumer, you actually have a couple options too. First option is you start out with main, and then main creates two threads, one for producer, one for consumer. You remember that from last time, right? The like POSIX threads, P threads you could do create, right? So then you attach a function to it. So the thread created runs that function. But how many threads do you have by creating two threads? Two? No. Main itself is a thread, okay? When you start running, you already have one thread, even if you don't do anything, because programs start out single-threaded anyway. So even without multi-threading support, you have one thread. By creating two, you actually have three threads, okay? So then you say, that's kind of wasteful, isn't it? I mean, if I want to produce and consumer, and if my main never really needs to do anything else, I should be able to just reuse main as one of the threads. Yes, you could. So that's option two. So, I mean, you could do one or the other way. So main can spawn just one thread, say consumer. And then main itself, after spawning the consumer thread, it itself can just call producer, right? So now you have two threads because you're reusing main's thread. Otherwise, main is not going to do anything, right? It just sits there, right? So, or even falls off and then exits. So that's wasted anyway. So, so this is more economical because you can reuse main's thread. So you only have to create one, but now you have two things running. So, I mean, it's up to you what you want to do. Now, the communication will be shared memory. So you do 1 byte data buffer to begin with, and then later you can do like bounded buffer, FIFO, and all that, right? And this just has a single flag to indicate whether data has been produced or consumed, right? So I mean that's a lot like serial port. And then of course, what we do with consuming is then we actually use serial port to indicate what's happening. And now, quick review of 8051. So it simulates a traditional 8051, or Edsim51 simulates a traditional 8051 architecture. And it is a Harvard architecture. Remember what Harvard architecture is? Separate memory for program and data, right? As opposed to conventional computers, which is called von Neumann architecture, sometimes called Princeton architecture, not von Neumann. It's N-E-U-M-A-N, and that's the German word. Actually, it's supposed to von. German V is pronounced F, right? But then in American kind of use this hybrid pronunciation. So von Neumann is the standard pronunciation. So don't call it von Neumann. It's von Neumann. Okay, so that's something called Princeton. But Harvard architecture is separate addresses for code and data. Very common for microcontrollers and DSP. So it has what? 64K of code memory, if you remember from my earlier intro. That's a lot. You can actually, you'll probably have a hard time filling up 64K of code because it's so economical, right? In code size. IRAM is only 128 bytes and used also by register, by stack, and whatever is left you get to use. There's no X data, and in fact 8051 can be compared without X data. So that's a separate bank for up to 64K, but it's not simulated. But we don't need it. Okay, and 128 bytes of IRAM, it has address 0 to 127 or 7F hex. So what do we do? Now, so one thing is, it is actually a good idea to make use of register banks. Remember register banks? So it's a way of mapping different parts of IRAM to these registers, R0 through R7. So by default, it uses bank 0. So address IRAM register, so IRAM addresses 0 to 7 get mapped to register R0 to R7. Now, if you use banking, you can have up to 4 banks. So bank 1, if you select bank 1, then direct address 8 through F get mapped to R0 to R7. So that means if you try to modify R0 when bank 1 is selected, then address 8 gets modified. All right? And so forth. Yeah, well, I'll get to stack. And so first, the register concept. Okay, so bank 0, 1, 2, 3. And what's the advantage to using bank 0 to 3? Well, it's actually nice because when you switch threads, you just switch bank. And that's just setting a few bits. And that way, it saves you the work of having to push and pop these registers, right? So saves code size, saves time, saves extra memory space. So I think it's nice. Okay, and so that way, so we do this differently from regular threads package. The regular threads package actually would have to do all the work of pushing your registers, popping your registers in a threads control block, right? TBC. Remember, there's process control block, threads control block, right? So, but then here you fill up pretty quickly. So, since they're already taking up memory, why not just use them and then have a faster switch? Okay, and 8051 does want people to use take advantage of register banks. So this way, you just have to set bits, but then you're limited to 4 threads, which is okay. I mean, you don't have that much memory. I mean, if you add up the stack, pretty soon you run out of space. So I think this is a fair trade-off. So let's just stick to this convention of using a bank for each thread. Okay, and so part of switching context is you actually have to switch bank, but that's not too hard. And you do have to allocate the stacks as well, which was just asked. So now let's look at the stack. So remember there was a stack which didn't assume multiple banks. because on power up, SP is 7, and so it's actually using space that would otherwise be used by bank 1. So this is not okay. So first thing you have to do, if you want to support threads, is you got to move the stack pointer out of the way so that these banks can be used, okay? But you have a chance to do that on power up. So, but anyway, you do remember push and pop, right? So push is pre-increment, so that's IRAM plus SP gets val, and then pop is post-decrement. So IRAM bracket SP minus minus. So the SP is that point there, right? And you can actually assign SP to another location that you want to use as a stack. So that's good. And we'll come back to where we want to put the stack. Now, PSW is what's called program status word or processor status word. I think there's different names for it, but really it's the same thing. On 8051, it contains a number of bits. What are they? So there's a C bit you may have seen, right? When you were doing like add subtract, right there with a sub B, sub with borrow. So when you do carry or borrow, like borrow is when you subtract a number that's smaller, right? And then you have to borrow. Well, that C bit is also called borrow bit. It would be set to 1, so you know that, that you were actually borrowing a bit, and you can use this to form longer integers. Or carry is when you shift things out and then it falls off. Where does it fall off? Oh, well, it falls off into the C bit. So these are individually addressable as well. And there's AC for auxiliary carry, that's for binary coded decimal. But if you're interested, you can look at it. Otherwise, I don't require you to know this. And then there's F0 flag, that's user usable. R0 and R1, which correspond to PSW 3 and 4 bits. These are the register bank select. Okay. So now the register bank select, that's to select bank 0, 1, 2, 3. 2 bits is enough for that. So by setting those bits, you actually remap the registers. Okay? And in assembly, you don't get to well, in assembly, okay. Assembly actually would have a separate bit address for these bits. So you could access either as PSW as a whole thing, and that would be 1 byte at a time. Or if you want to go into individual bits, there's actually a separate address for each bit. And so you have to use bit instruction to address those bits. You know, it's not automatic. you can't say PSW.7 and expect it to work. No, somebody has to define the mapping of the bit address to the bits in the SFR. Okay, but okay, that's fine. It's all taken care of. If you want, you can look at 8051.h to see how they define it. Anyway, you can use these names. These names are actually known to SDCC. And OV for overflow, P for parity, that's in communication or for the other checks. So anyway, so yeah, these are, you don't have to know all the details, you have to know the register select bit 0 and 1 are part of this. The carry bit, which is used quite a bit, also is in PSW. So to be safe, the whole PSW should be saved and restored as part of the context.